class, welcome back. So last time we were talking about orders of elements of groups, and just to refresh your memory, we defined the order of an element G as the smallest positive power of G that's equal to the identity element in the group. So today we're going to be continuing that discussion, focusing mainly on one particular theorem about orders. Before getting to that theorem, though, I want to start with a caution, which is that just because G raised to some power K is equal to the identity doesn't necessarily mean that K is the order of G. So to give a specific example, like if I have an element of a group in my hand and I see that when I raise G to the 8th power I get the identity, that doesn't necessarily mean that the order of G is equal to 8. And the reason that's the case is that there might have also been a smaller power of G that I could have raised it to that would have given me the identity. For a specific example, let's say G is the set of numbers 1, -1, I, and -I, which is a group under the operation of multiplication. Then one thing we talked about in the last video is the fact that the order of I is equal to 4. Because if I start raising I to powers, the first time I'll get 1 is when I do I to the 4th power, which is equal to 1. But that's definitely not the only power of I that equals the identity. You can check if you'd like that also, in addition to I to the 4th being 1, I to the 8th is equal to 1, and I to the 12th is equal to 1, and so on. If you'd like to check that, I encourage you to pull up a calculator or Wolfram Alpha or your favorite way to do calculations and make sure that I'm telling the truth about these powers of I being equal to 1. So again, the point that I want to make in this example is that if we hadn't yet known the order, but we just happened to notice that, say, I to the 8th is equal to 1, we might be led astray and think the order of I is equal to 8, and we wouldn't quite be right there because there's a smaller power of I that's also equal to 1. So our main theorem for today is a statement that says, okay, well, exactly which powers of an element really are going to give us the identity? Here's the statement. It says, let G be any group and let little g be any element in that group. Then little g raised to some power K is going to give me the identity if and only if the order of G divides that power K. So the order of G may not be equal to K, but what I can say is that the order will divide K. So to connect this back to the previous example, in that case our element lowercase g was the number I. We mentioned that I to the 4th is the identity, I to the 8th is the identity, I to the 12th is the identity. And if we look at those powers and remember that the order of the element I is equal to 4, we'll see that that order of 4 divides all of those powers. It divides 4, it divides 8, it divides 12, and then according to this theorem, we can also expect that I to the 16th is going to be the identity, and so on for any multiple of 4. Okay, so the proof of this theorem, I should warn you, is probably going to be the most involved proof we've seen thus far. And to lead into it, let me just give a brief little interlude to make sure that we all know what the structure of the proof is going to look like. So first, let me remind you that structurally, if we were proving a statement of the form P implies Q, the way that proof would look is we would suppose P, then argument, 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 and eventually in the end, we would conclude that Q was true. But what we'll be doing in the proof of this theorem is one step beyond that. We're proving a statement of the form P if and only if Q, and that should always have two parts. First, we'll prove P implies Q by following the template in the first bullet point here, and then second, we'll prove the converse, that Q implies P. So let's now apply that template to the theorem on the previous slide. So at the top of this slide, I've just rewritten as a reminder to you what it is that we're trying to prove. We're trying to prove that g to the k is equal to the identity if and only if the order of g divides k. And so following the template on the previous slide, we'll first prove the implication if g to the k equals the identity, then the order of g divides k. And so the way we'll begin that is by supposing that g to the k is equal to e. And our goal now is to argue that the order of g must divide k. Here's a clever trick that we can apply. So we want to know that the order of g divides k, and so what we'll do is we'll take k, we'll divide it by the order of g. We don't yet know that it's going to go in evenly, which means that we might be left with both a quotient and a remainder. What that's saying is that k is going to be equal to the order of g times some number, and that's the quotient. If it went in evenly, we would just stop there. But since we don't yet know that it goes in evenly, we may have something left over, and that's what I'm referring to as the remainder. So here at the top of this slide, I've rewritten that last equation that we had, and now I want to make one key point about the remainder, which is that the remainder is always going to be an integer that's somewhere between 0 and strictly less than the order of g. That's a statement about dividing one number by another. So for example, let's say we were dividing 11 by 4 and we wanted there to be a remainder. Well, there will be a remainder of 3 in that case. And the thing to highlight about that remainder is that it's somewhere between 0 and strictly less than the thing we were dividing by, which in this example is 4. In the general context of this proof, the thing we're dividing by is the order of g, and so the remainder we're left with will always be something between 0 and strictly less than the order of g, the thing we're dividing by. To see why that's important, let's go back to what we were assuming. So at the beginning of this proof, remember, we assumed that g to the k was equal to the identity. Now using the equation that's at the top of this slide, I can replace k by the order of g times q plus r. So I'll make that substitution. Next, I can use familiar rules of exponents to break up this complicated exponent as g raised to the order of g, all raised to the q, times, or I should really say star, depending on what the group operation is, g raised to the rth power. And the right-hand side of this equation is still e. But now notice here that I have g raised to the order of g. And by the definition of order, if you take g and raise it to its own order, you'll always get the identity. So actually what I have here is e raised to the qth power, and it doesn't even matter what q is. The identity raised to any power is always the identity. So that thing that I've circled in yellow there is one big copy of the identity, meaning that we can ignore it, and what we'll be left with here is the equation g raised to the rth power is equal to the identity. Okay, I'm out of room on this slide, but when I flip to the next slide, you'll see that what we'll do is we'll combine this statement here, labeled key point, with this last equation we have here to get the conclusion, at least of this half of our proof. Namely, we now have that r is strictly less than the order of g, and yet g raised to the rth power is the identity. Well, we thought that order of g was supposed to be the smallest positive power of g that equals the identity. Now I'm raising it to a power that's even smaller than the order of g and getting the identity. How is that possible? It's possible because the order of g is defined as the smallest positive power that equals e. So if I'm raising g to any smaller power and getting e, the power I'm raising it to must not be positive. That is to say, r must not be positive, so r actually must be 0. So if we go back to our equation, k is equal to the order of g times q plus r, that plus q goes away and we just see k is equal to the order of g times something, which in other words means that the order of g divides k. I know we've gotten far afield at this point, but if you look back, you can remind yourself that this was exactly what we needed to prove in order for this implication of the theorem to hold. So we're done with the forwards implication. Good news is the backwards implication is much shorter, so let's do that now before we're done with today's video. For this implication, we'll suppose that the order of g does divide k and try to deduce that g raised to the kth power is the identity. Well, what does it mean to say that the order of g divides k? By definition, it means that k is equal to the order of g times m for some integer m. So if we raise g to the kth power, we can re-express that as g raised to the order of g times m power, which we can break up using rules of exponents in this way. Then again, we can notice that g raised to the order of g by definition is the identity, so this is really identity raised to the mth power, which regardless of what m is the identity. So we've successfully proven that g to the k is equal to the identity. That completes the reverse implication and at long last completes the proof of this theorem. This theorem is going to be super useful in allowing us to efficiently compute orders of elements in groups, which is sort of our long-term goal. We'll start working towards that goal in the case of the symmetric group in your worksheet for today. So I'll see you in class.